Um, welcome. I pride myself on making videos that are moderately funny. Yeah, fun to watch probably, and mildly educational. And since I now have glasses, you know that it's definitely good education. This is a rebranding of a previous playlist of videos with one video in it. So instead of Y, it's being rebranded as the 5Ws and the H. 5Ws and the H. Yes, 5Ws and the H. Which is a really cool band name, probably, if you have 5Ws and a H. H&TheWs. That's a band name. There you go. I've switched which light I'm using, so hopefully there's enough light to see me, but there's less glare on the board. Because I used to have that, which is gets in the way quite a lot. So hopefully that's okay. Okay, so yes, welcome to H and the 5Ws, where our topic this week is tectonics. That may be spelled wrong. Fact checker. It's also me, by the way. Yeah. Tectonics. Right. Okay. So tectonics comes from the Greek for something related to building. So it's often defined as the architecture of the Earth's crust. Yeah, the Earth's crust is the top layer of... Okay, so this is our Earth. Better? This is our Earth. Well, not entirely. This is 7/8 of our Earth. Imagine you just sort of like take out an eighth and it's just like floating off in space somewhere over here. So this is like a cross section. If you cut it down that way and then that way and then that way, yeah, and you take out an eighth, this is what you would see. So I don't know how well the colours are coming out, but there's a very thin strip around the edge. All of this with the white in the middle, that should all be red, but I need to do something in the middle in a second. And then this orange band, and then a blue bit, because I didn't have a silver. Yeah, these are the four basic layers of our Earth. The outer edge is the crust, so that's the bit that we stand on, where all of the tectonics take place. Well, no. Where all the land is. So that's all the bits that are moving around on the top. This is superheated rock, which is so hot that it's liquid, but there's so much compression. Well, not really. It's still sort of liquid, but there's a lot of compression, so it's sort of solid because all the molecules are so close together. And then these are boiling hot. So this is the outer core, and that's the inner core. Very stylistically interpreted by my wonderful self. Should have taken art. That is a joke. Don't yell at me in the comments. Where was I? Yes, so these bits are phenomenally hot. They are so hot that they'd probably be a gas if they could. This is essentially just molten iron, but it's so compressed by all of this weight pushing down on it that all of the molecules are so tightly packed together that they can't move. So technically it's a solid, but technically it can be classed as a solid, but is still in liquid form, which is called, from the top of my head, so this section, which I'm not naming yet, is semi-solid. So that's the compressed bit that I mentioned. This is a liquid section, and that is actually solid, because it is just compressed. So solid, semi-solid, liquid, solid. The main centre area is straight iron, just a full ball of iron with like the tiniest bit of silicon, I think it is, on the inside, like mixed in. So yeah, that's the general structure of the Earth. And then if we zoom in to... Okay, I've had dinner, so I'm now older and therefore wiser. Past me is a fool, silly fool. We're not zooming in yet, and when I said that this was iron and a tiny, tiny, tiny little bit of silicon, it's nickel, not silicon. Iron and nickel. Two magnetic things. Two of the three. The other magnetic one is zinc. I have a periodic table up there. So if you see me just doing that, yeah. So yeah, we're not zooming in yet, and we're still on this. We're on layers now. So this is called the crust. This is called the mantle. Outer core, inner core. Now these, they're very exaggerated, the proportions. So these are actually, well, there's also a lot of variation between this, on the crust especially, there's a massive difference. It's like between 5 and 70 kilometres difference in some places. So we'll just label that up here, 5 to 70. There, you can probably see that. You can definitely see that one. Okay, so 5 to 70. The mantle is slightly bigger than that. It's 290 kilometres. It's 2,900 kilometres thick. It's about 47% of the entire radius of the Earth. So it's a bit chunky, yeah. The outer core is slightly less than that. It's 2,200 kilometres, and the inner core is cut that bit out. On average, it's about 1,350 kilometres, give or take a bit. Okay, so that's, yeah, it's a little bit stylised. That, yeah, the proportions are a bit off. Anyway, now here's the bit where we zoom in, and you get something that looks a little bit like this, where this is the generally assembled core, so this is both outer and inner, somewhere around here. Mantle is all of this bit, and the crust is the tiny little crust on the top. Sort of like an apple skin on the apple of the Earth. Now it's split up into parts, so like a jigsaw puzzle. And all of the pieces fit together well, but there's like boundaries between them. This is slightly exaggerated. They're like microscopic. Well, no. Some of them you can see, they're like massive, like triple my arm span. There's one in Iceland that I went to, which I'll put a picture up now.
I couldn't find my picture of when I went, so here's a random one from a newspaper.
If I can find it. Somewhere around now. Should be there. Good? Yes? Okay, nice. So, that one in Iceland is massive, but there's a bunch of actual, like, ground in between it. It's not just like a chasm cut into the earth. Yeah, so that's these bits. Slightly exaggerated. Now, the temperature of this bit, well, the crust doesn't matter for temperature, core doesn't matter for temperature, but up here, it's a mere roughly about 1,000 degrees Celsius. Just a mere amount, which is about 1,800 degrees Fahrenheit for you American people. Sorry. Now that's hot, right? That's, yeah. Between the core and mantle, this area is roughly 3,700 degrees, which is a little hotter than that. just a tints in it. Probably about the temperature of an easy bake oven. For you Fahrenheit people, that's about 6,700 degrees Fahrenheit. That's hot. That's a little bit hot. Okay, so I've tidied this up a bit, shifted the things over to the side. I've also added this, the centre of the Earth. I thought while I was doing temperatures for stuff, might as well have a look at this. Now, the temperature for this tiny little dot is, get ready, 5,500 degrees Celsius. Now, might have a little bit more kick in Fahrenheit, because this is 9,930 degrees Fahrenheit. A little hot. That is almost the temperature, actually it is roughly the temperature of the surface of the sun. Right there. Yeah. kind of makes sense now why stuff is so hot, why this is hot, why that's hot, and why you can still feel heat from the ground all the way up here, like 6,000 kilometers away. Well, not 6,000. Yeah, 6,000. 6,000 kilometers away. Because that is the same temperature as the surface of the sun. Just a cool little factoid, thought you'd like. But moving swiftly onwards. So there's a big difference between 3,700 and 1,000. 2,700 to be precise, as the distance. So it roughly drops off one degree every kilometre you go up, which is quite good actually, for heat retention. How that happens is, if you've ever... Okay, yes, soup. When you're boiling soup, not boiling soup, you shouldn't be boiling soup, I think. When you're boiling soup, the flame is on the bottom of that. There's all the flame there. Then you have your pot. Hang on a second. Diagram time. Okay, I'll stand over here. When you're boiling soup, you've got your fire on the bottom, so that's the really hot stuff, and it only comes into contact with this bit. However, eventually the soup warms all the way through. So you'd think that if it just stayed still, then the bottom bit would just get really hot. The top bit would get hot as well, but the temperature difference between them would just be astronomical. You'd have like burnt bits stuck to the bottom, and then like barely warm stuff at the top. And it would be absolutely horrible. Never make soup for anyone. If you if you manage to break physics and keep this not moving, never make soup for people. They'll hate you. So that's what happens here. You have your really hot bit, which is your flame, your cooker, your stove, whatever, and then this is the top of your soup, where hopefully not the crusty bit on the top of your soup goes. So somehow this can't stay. It just can't stay where it is. You can't just have this be static. So somehow it needs to move around. So what happens is all of this superheated material, right here, all of that iron, no, iron's the core. Actually silicon, that's where I was getting confused earlier. Sorry, pardon me for insulting you. You sort of knew what you were talking about. So this is iron and nickel. This is silicon, sort of. Some variations of silicon. 3, I think. So all of this silicon and solid rock, it all gets really hot down here. Now, as you probably, most likely, definitely have heard, heat rises. So what this does is it goes from here and goes up. It goes up, it keeps going up, and as it goes up, it cools down, because it just does. It's further away from here, so it loses the energy that it gained from here, from being really, really hot, so it's moving really, really fast. And as it moves up, it loses that energy, because it's moving, it's having to like push all the stuff above it out of the way. If you imagine, if you've ever been stuck in like a ball pit or anything, you've dived into the bottom, you have to like push out the top. You can't just like stand up. So this expends a bunch of energy, which is why there's such a big difference between the crust core, no, mantle core boundary and the crust core. Mantle core, crust mantle boundaries, there's such a big temperature difference because once the rock in the mantle rises, it loses a bunch of its energy. Now what this does is now you have a really dense bit up there, because if you imagine up here is like a carrier bag and you have some stuff in it, and then someone passes you a towel and you stuff it in, it gets really tight in, and then you stuff another one in, and another one, and another one, and you keep going. Eventually the bag will burst and everything will go everywhere, off to the side. That's what happens. So this goes off to the side because it's being pushed away by all of the stuff coming up behind it. So it goes off to the side and then sinks as it's now colder than the rising stuff. It's pushing out of the way and it sinks back down, all the way to the bottom. You get the idea. Until it gets back to the bottom. Well, here you have cold stuff dropping down, 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 and as it gets closer to this bit, it heats back up again. So, well, essentially, if you imagine the towel on the bag, you have a cupboard that's completely empty because you've stuffed all of your towels into a bag. So as it's coming back down, there's a bunch of space in that cupboard. So the towels just whoosh into the space, well, obviously not, but yeah, you get the idea. So there's a vacuum here, really dense up here, so it moves out of the way, drops back down, and then fills in the vacuum, and that happens over and over again. So none of it's like empty space. It's not actually very dense up here, and it's not actually very vacuumy down there. It's just less dense and more dense. And that happens both sides. So it happens both sides, and you'd have other ones like here and coming down there. So you'd have bits going up there, and then it joins into there, and then bits coming off there, and then also bits coming up here, going around into there, and also coming off there. So the entire mantle, all the way around the centre of the Earth, no, around the outside of the core, is just this. It's all going up and then coming back down again, going round and round and round, forever, basically. And it transfers the heat from the bottom to the top, and it keeps it all moving round in place. Now, what you might have noticed is this. Those. They're right bang splat. Right there. Right there, where all of the stuff is. It's all churning underneath. Oops. The mantle is all churning underneath the crust and pushing and pulling, and there's stuff converging in place. And this crust isn't linked to anything. It's not like connected to all the other bits of crust around the outside, and it all stays still while this is moving. The bits on the crust move as well, and those are called tectonic plates. We finally got to tectonics. Well, we finally got to the word tectonics. This is all tectonics as well. So this is essentially tectonics. Okay, so this is a small scale model of what I was talking about. So you've got your tectonics and all of the mantle moving underneath the plates of the crust. Now, the plates move with the mantle. So here, they're going together, ramming into each other. Here, they're also doing that, so they're going together. Here, you have a really hot plume. It's called a super plume. Well, it's called a plume when you have a normal one of these. But some places, you get super plumes. So those are really hot, superheated magma from the crust, from the mantle. I'm terrible with words. I don't know why I'm trying to do this. Yes. Okay. So super plume here comes up, and it's so hot that you get a build-up of heat coming all the way up here, and it reaches here, and it's so hot it melts its way through the crust until it pops out the top here. Not like that, obviously, but it breaks through the crust in the middle, and that's why you get places like Hawaii, which is a volcanic island formed on a superplume. So that it doesn't split the plate in half, because if you imagine this as a top-down view of a plate, it would just be there, so it's still held around the edge. So you have superplumes there. At this point, this intersection, the plates are smashing into each other, and they cause friction between each other. So they're rubbing against each other, smashing into each other, and some goes down, some goes up, some are the same and they both go up, and some both go down. And yeah, so that's one type of plate movement. Now, here are the other two, as well as the crushy one. So these, well, that one's going that way as well. So this is plates. This is one plate, this is another plate, that's the third plate, that's the fourth plate. There's other bits around it, but that's the basic model. So this plate is moving this way, this one is moving that way, that one also that way, that one also that way. So this boundary here, they're crushing together, and that's called destructive. It's a destructive boundary. So, destructive. Right there. This, so as they go together, they're breaking apart, and some are going underneath the other crust, so they move like that, and then this one breaks and gets melted in the mantle. So it melts, and it's essentially the plates are being destroyed as they hit into each other. This is constructive. That says that, trust me. Because as they move apart, it makes space in. If you imagine these are the plates, you've got the hot mantle under here. As these move apart from each other, there's now space in the middle for all that magma that's really hot to rise up through the gap, and as it rises, it solidifies in the middle, and then it forms more plate, so that's constructive. So that's destructive because it's breaking them apart, and this is constructive because it's making new bits of plate. This is a conservative. Hang on, fact checker. Yeah, conservative. I don't know why I doubted myself. So this, the three types are destructive, constructive, and conservative, because they're just moving past each other and they're not breaking into each other or pulling apart. So these stay at the same distance. Now, this is getting on a bit. This is the basics of tectonics. So, in this episode, I've described how the mantle, well, the structure of the Earth, from the crust, the mantle, which I keep messing up, to the inner core, to the outer core, to the inner core. You know, you were here. I don't, I've been here for longer. Crust, mantle, outer core, inner core. There. So that's the 4 layers. We've run through temperatures, what they're made of. So, rock, more rock, rock, and rock. We've talked about how the heat rises with the magma, and how that moves all the plates around on top. We've talked about the 3 different types of plate boundaries, and in the next, what did I say I was going to call it? H&TheWs. In the next H&TheWs episode, which I'm going to film in like 2 minutes, we're going to go into the 2 things that can result from these boundaries. So, see you then.